So our next talk is about soft and stretchable electronics with liquid metal by Professor Carmel Majidi from CMU.
Thanks. I appreciate so much. So it's a pleasure to be here. I'm here from Carnegie Mellon University, and what I'm going to talk about is actually from my research group here. It's a pretty diverse group of engineers and scientists, and also kind of touch on some of the collaborative work I'm doing with Mahmoud Tabakoli's group at Coimbra University in Portugal. And then I'll kind of touch on also some of the work done by a spin-off company, Arieka, that's working on commercializing a little of what I'm going to show. Right, so really the focus here is on liquid metal. This is something I'm sure a lot of you are familiar with, and maybe have kind of explored a little bit in terms of your own work. These are metals, typically a eutectic blend of gallium and indium, a metal that's liquid at room temperatures, so very low viscosity, just a little bit higher viscosity than water, and high electrical conductivity here. So a lot of different, especially kind of in the academic domain, a lot of different applications and kind of studies on uses of liquid metal for especially kind of soft and wearable electronics, and also kind of mechanically deformable antenna. I'm going to largely focus on uses of liquid metal for printed soft electronics. So electronics that are very thin, highly flexible, and also quite stretchable. Okay. So the some of the original kind of work with liquid metal, I'll just kind of run this video here. It doesn't look like the codec's available. So anyway, what you should see here is a little strip of rubber with a microfluidic channel of this gallium-indium eutectic. As you stretch the rubber, basically because the metal is liquid, it kind of stretches and deforms. Now this is a microfluidic channel. This is kind of produced through injection filling. We can also pattern liquid metal using laser ablation. So this is work on thin films of liquid metal on a chromium and copper thin film, all on a soft silicone rubber substrate. So we can make soft and stretchy circuits that way. And if this video runs here, let's see if it does. There you go. You can just kind of get a sense of kind of what these circuits look like after we pattern them, and we can just kind of pop on the chips. And the liquid metal doubles as kind of like a solder that we can use to kind of mount these surface-mounted IC chips. So again, quite soft, quite stretchy. The metal interconnects stay quite conductive, even under strain and mechanical deformation. Here we have a digital circuit with the 9-axis IMU and also a temperature sensor. So this is kind of nice in terms of early demonstrations that we were able to show with liquid metal. But the limitation here is that this is all kind of lithographically patterned, either requires kind of photolithography or uses laser and micromachining. Really kind of our hope was to kind of make versions of this that are kind of a little bit more compatible with some of the kind of the printed electronics approaches. Here's just kind of another example of really kind of pushing the limits in terms of stretchability with these kind of thin film kind of liquid metal circuits. So kind of moving to an architecture that is more compatible with printed circuitry, we shifted from having just thin films of liquid metal to having dispersions of micro and nanoscale droplets of liquid metal within a soft rubbery substrate. So typically we use silicone rubber. This also works with urethanes, fluoroelastomers, polyacrylates, pretty much any kind of soft polymer out there. If you have a high enough density of these liquid metal droplets, and again, these are kind of more microscopic, somewhere between 100 nanometers to about a micron, 10 microns in diameter, we can actually form percolating networks of these droplets and get conductive pathways. As you can see here, even at 50% by volume of liquid metal, so very high concentrations of liquid metal, we don't really alter the mechanical properties of the rubber. In the case of silicone, it still stays soft. Young's modulus below 100 kilopascals. Still remains stretchable. Its strain of break is beyond 600% strain. And it has very high fracture toughness. So adding liquid metal actually enhances the durability and the tear resistance of the rubber on account of the kind of those microscale droplets and the heterogeneity that comes with that. So just very quickly, I want to mention one feature of these composites is that if we have a high concentration of droplets and they're not touching each other, we get rubbers that are electrically insulating but thermally conductive. And we actually approach metal-like thermal conductivity. This didn't kind of render properly. Sorry for this. I'll just kind of skip ahead here to this next slide. This actually highlighting some of the work we're doing